So hello again. Today's lecture is going to focus on chapter 37, which is the early quantum theory and models of the atom. So this was going on, at least initially, more or less concurrently with Einstein's work on the special theory of relativity. In fact, you'll see that Einstein contributed to quantum theory as well, at least in the context of the photoelectric effect. So let's start by talking about the um, state of physics, besides relativity, in the late 1800s and early 1900s. So in the early 1860s, James Clerk Maxwell established that light is an electromagnetic wave, but there was some discussion on whether, the waves could also exhibit particle-like qualities. And allowing electromagnetic waves to act like particles made it possible to explain what was observed at the atomic level. And one of the things that this led to was the idea that energy changes are in specific steps or in quantized steps, so that there's no gradual continuum of possible energies, but rather that energy jumps from one state to another, and that these are quantum jumps, that there's a measurable distance between one energy state and another energy, or a measurable amount of energy between one state and another state, and that these are things that could be observed. So, um, Stefan's law, and this, you probably covered this in thermodynamics if you took physics 3. Stefan's law showed that the energy emitted by a black body, and so a black body is sort of this idealized object where that absorbs all energy that's incident on it, and then emits the energy back out, and that the energy it emits is essentially proportional to the fourth power of the Kelvin temperature. But it turns out that this radiation also has a wavelength dependence. So you're not just emitting radiation, at a uniform level with no wavelength dependence, that there is a peak wavelength and there is a region of wavelengths where it emits a lot. And then there are other regions in the electromagnetic spectrum where the object doesn't emit radiation all that intensely. And where these wavelengths are depends on temperature as well. So Max Planck was able to explain black body radiation by assuming that the black body consisted of vibrating bodies with discrete energy states. So the energy states are equal to n, which is an integer, multiplied by f, the frequency, and multiplied by a proportionality constant that's since become known as Planck's constant. And Planck's constant in SI units is equal to 6.626 times 10 to the negative 34 joule seconds. So not necessarily a large amount, but something measurable. Planck, starting with that assumption, was able to derive an equation relating the intensity of radiation per nanometer of wavelength to the Kelvin temperature. And so you see this ugly looking equation: the intensity equals 2 pi hc squared, where c is the velocity of light, lambda to the negative 5, where lambda is the wavelength in meters, divided by e to the hc over lambda kt minus 1. And you can actually integrate this over all wavelengths to then get back to Stefan's law. The relationship between the wavelength of peak intensity and Kelvin temperature is given by Wind's law. So the peak wavelength times the temperature is equal to 2.90 times 10 to the 3 meter kelvins. And so keep in mind, this intensity is, the intensity is watts per square meter per nanometer of wavelength. You can also write the intensity as watts per square meter per hertz of frequency or per inverse centimeter of energy. So you'll see it written different ways in different contexts. And actually, the peak changes on what uh, how you define those units. And I'll show that in a couple of seconds. So again, you have this relationship, and then the peak temperature, or rather, the wavelength that produces the peak in intensity is directly related to temperature, so that the product is essentially constant. So you double the Kelvin temperature, you divide the peak wavelength, or the wavelength where the intensity is at a peak, by two. So how does this look in practice? And you could set up a computer code and run that function and get this coming out. And so with 3000 kelvins, you have a peak a bit less than one wavelength. At 4000 kelvins, you have a much sharper peak in intensity, and the wavelength is about um, uh, zero point 0.6 or zero point 0.7 microns or micrometers. At 5000 kelvins, you have an even sharper peak still, and that's at about 0.55 microns or 550 nanometers of wavelength. And so you can see how the wavelength keeps getting shifted, or the wavelength where the intensity is at peak keeps getting shifted downward. And you can see how different this is from classical theory. So quantum theory did a much better job of explaining observations than classical theory did. Now, part of the utility of blackbody radiation, or blackbody theory, even though it's works with idealized objects, it has some real life applications. So the orange line here is the blackbody spectrum of an object with a temperature of 5,780 kelvins. And if the red line superimposed on this is the solar spectrum, and you can see that the sun emits radiation at a rate comparable to a black body with a temperature of 5,780 kelvins. So that tells you something about the sun's surface temperature. Internally, its temperature is actually quite a bit hotter, but the sun's temperature is approximately 5,780 kelvins. The drops in the emission spectra correspond to wavelengths of substances that are located within the sun's atmosphere, such that those wavelengths get emitted, but they don't get out of the sun's atmosphere because there are materials in the sun that can absorb them. So the sun can be approximated as a black body fairly well. And not only can the sun be approximated as a black body fairly well, but the Earth can be approximated as a black body also. And so this is the emission spectrum of the Earth. Notice, and also to get back at the wavelength dependence. So the wave number is basically 10,000 divided by the wavelength. And that gives you the wave number in inverse centimeters. And then 10,000 divided by the wave number in inverse centimeters gives you the wavelength in microns. So you notice the spectrum. Notice here it's watts per square meter per inverse centimeter. And so that peak is at a larger wavelength than watts per square meter per nanometer would be. And so you're not measuring exactly the same thing when you're talking about watts per square meter per inverse centimeter or watts per square meter per nanometer. So keep that in mind, that the spectrum gets shifted towards higher wave number, and also or towards lower wave number and higher wavelength if you're using per inverse centimeter rather than per nanometer of wavelength. And so inverse centimeter is approximately a unit of energy. And we'll talk about why that is in a couple of minutes. So again, getting back to the Earth's spectrum, notice the smaller wave numbers. These correspond to higher wavelengths. So 1,000 inverse centimeters corresponds to 10 um, microns of wavelength. And the 400 inverse centimeters corresponds to 25 microns of wavelength. Whereas over here, the 10,000 inverse centimeters corresponds to 1 micron of wavelength. The 20,000 inverse centimeters corresponds to 0.5 microns of wavelength. So you can see the difference. So these are much lower wave numbers, which correspond to much lower energy, which you would expect when you're talking about the emission spectrum of the Earth as opposed to the emission spectrum of the sun. So the Earth emits electromagnetic radiation as well. It's not at wavelengths that our eyes can see. Our eyes, human eyes in general, or in particular, animal eyes in general, evolved to be sensitive to the wavelengths of radiation that the sun emits, not that the Earth emits, because um, again, though those are the most intense wavelengths, um, at the Earth's surface. And so, I mean, it's not surprising that that's what our eyes evolved to be most sensitive to. So the sun's radiation more so than the Earth's radiation. But the Earth's radiation, outgoing radiation, and the sun's incoming radiation are ultimately, at least approximately speaking, in balance. If more radiation is coming in than is going out, the Earth gets warmer. And if more radiation is going out than is coming in, the Earth gets colder. And that works on small scales like weather, for example. That's why it cools off at night and warms up during the day. And but it works on longer scales than that as well. And so when we talk about climate change, we're talking about adding to the things that absorb infrared radiation. So you can see the different absorption bands that are within the Earth's emission spectrum. So there's certain gases in the Earth's atmosphere that emit the kind of radiation that the Earth, or that absorb the kind of radiation that the Earth emits. So this diagram comes from one of the early weather satellites called the Nimbus satellites, and there was this series of them. And so they measured the Earth's infrared emission spectrum. And so you see the black body curve. This corresponds to 320 kelvins. That's actually pretty hot, but that corresponds to a location over the Sahara Desert. So you've got this very hot surface temperature. And so you have this strong emission, but you've got gases keeping most of that emission from getting out into space. So you have multiple bands where there is water vapor, for example. And then you have this one band between 9 and 10 microns where ozone absorbs a significant amount of infrared radiation. You also, between about 7.5 and 8 microns wavelength, have methane, CH4. And then where the Earth emits its peak radiation, at least in terms of watts per square meter per inverse centimeter, that corresponds to a wavelength of about 15 microns. And that's right in the heart of an absorption band of carbon dioxide. And so that, when we talk about climate change, the single biggest contributing factor is carbon dioxide for that reason, that, it absorbs the radiation that the Earth emits, at least in terms of watts per square meter per inverse centimeter, at the greatest amount of intensity. And you can see how much of that the Earth absorbs. And as you add CO2 to the atmosphere, this line goes down a little bit further because more radiation is being absorbed, and that energy stays within the Earth's system. And that's why we have, that's why the planet gets warmer. So let's do a problem. Estimate the peak wavelength radiation from ice at 273 kelvins, a flood lamp at 3,500 kelvins, helium at 4.2 kelvins, and for the universe at 2.725 kelvins, assuming black body omission. So, in what region of the electromagnetic spectrum is each? So, let's set this up on the whiteboard. So again, we're going to be using Wind's law. So the wavelength, the peak wavelength multiplied by the Kelvin temperature, so the temperature has to be in kelvins for this to work, is 2.90 times 10 to the negative 3 meters Kelvin. And so the first thing is ice at 273 kelvins. So obviously this is the freezing point of water. You're not expecting it to be you're not expecting it to be very energetic, which means it's going to have a fairly high wavelength. So doing the calculation, so you get 1.06 times 10 to the negative 5 meters. So that's about 10,000 nanometers. So we think of, visible light goes from 400 to 700 nanometers. So this is in the infrared. Anything above 700 nanometers, which is the edge of the visible spectrum and the red edge of the visible spectrum. Anything above that in terms of wavelength is considered infrared. And higher wavelength corresponds to lower energy, which we'll talk about in a little bit in some detail as we move on. So then we have a flood lamp at 3,500 kelvins. So now you think flood lamps, well, obviously a significant portion of the radiation that a flood lamp emits is going to be visible. That's the whole point of the flood lamp, and it's the point of incandescent bulbs in general. But where is the peak of the radiation? And so that's, again, you set that up, and that's 8.29 times 10 to the negative 7 meters. That's still in the infrared. That corresponds to 829 nanometers. That's still in the infrared. But you get, from these lights a fairly white, a white glow, because you still have a pretty high intensity all the way through the visible spectrum. But the peak is still in the infrared, and that's part of the reason why incandescent bulbs are considered to be very inefficient. Most of the energy emitted by incandescent bulbs we can't see, so it's wasted energy. And so that's where the idea behind LED bulbs and compact fluorescence, although I guess compact fluorescence, or the more current technology that is, they emit much less energy overall, but it's still at visible regions of the spectrum. So it's less energy, but it's still the same amount of visible light. And that's the basic idea behind that. And then we look at we go to the very cold end. So helium at 4.2 kelvins. And so and that corresponds to 6.9 times 10 to the negative 4. Definitely still in the infrared. So again, the greater the wavelength, the smaller the amount of energy. And we'll talk about the math in some detail in a few minutes. And then you get the cosmic microwave background. We'll talk about that, the microwave background, in more detail in the last chapter that we cover, which is chapter 44. In the meantime, that's 2.725 kelvins. So that's 1.06 times 10 to the negative 3 meters. So again, it's all of this is in the infrared spectrum. And so you're not going to see any of this radiation. Here, for the second one, the flood lamp, the peak in wavelength, or the peak wavelength, at least in terms of watts per square meter per nanometer of wavelength, is at 8.29 times 10 to the negative 7 meters, or 829 nanometers, which is just a little bit into the infrared. But again, the spectrum is such that it still covers, a significant amount of wavelength gets emitted in the visible spectrum, which is why we see the white light. And basically, an incandescent bulb works the same way. But again, because so much of the radiation is emitted at wavelengths that we can't see, it's wasted energy, basically. Okay, so now we're going to talk a little bit about the photoelectric effect. And so let's see if I can get up a video for you. Okay, so we're going to watch a video, and this is basically explaining the photoelectric effect. And Einstein published this the same year he published the special theory of relativity. This is what got Einstein a Nobel Prize.
This tutorial will cover the photoelectric effect. Light exhibits wave-like properties, such as diffraction and interference. As a result, at the end of the 19th century, it was generally accepted that light was a wave. However, when studying the photoelectric effect, light appears to exhibit particle-like properties as well as wave-like properties. The photoelectric effect is the effect whereby when light is shone on a metal surface, electrons are given enough energy to escape from the surface. The way in which the electrons escape can be studied with this equipment. Two metal plates are arranged, with one of the plates exposed to the light source. The electrons liberated from the metal travel across to the other plate, causing a current to flow. This is known as the photocurrent. The photocurrent is detected as soon as the light turns on, suggesting that light is acting as a particle. If light were a wave, the energy would build up slowly on the screen. The particles start knocking electrons off the surface as soon as the light is switched on. It was found that the photocurrent flowed when ultraviolet light was shone on the metal, but not when the red light was shone on the metal. This was observed no matter how intense the beam of red light was. This suggests that the light is made up of particles which have an energy that depends on the frequency of the light. This can be demonstrated by analogy. If you fire a high-energy photon at an electron, you will liberate it from the metal. Correspondingly, if you fire a cannonball at an elephant, you will knock it over. In the same way, no matter how many low-energy photons you fire at an electron, you will not release it from the metal. Correspondingly, you can hit ping-pong balls at an elephant as long as you want, and you will never knock it over. The energy needs to be delivered to the elephant in one go. So now we've established that light is a particle, we can study how the energy of the photon relates to the frequency. When the electron absorbs the photon, it gains all the energy of the photon. The electron then expends some energy, escaping from the metal. This energy is called the work function of the metal. The electron then has the energy of the photon minus the work function of the material. So hence the relationship between frequency and the energy of the photon can be found through a simple experiment. If a potential difference is put between the plates using a variable power supply, then the electron not only has to escape the metal, but also traverse the potential difference in order to reach the other plate and cause a photocurrent to flow. The energy of the photon therefore needs to be larger than the work function of the metal plus the energy lost in traversing the potential difference. Otherwise, the electron cannot make it to the other plate. The energy lost by the electron in traversing the electric field is the charge of the electron times the potential difference. Hence, if the energy of the photon obeys this inequality, then a photocurrent will be detected. The photons deliver enough energy to the electrons to leave the metal and traverse the electric field. On the other hand, the voltage is increased, so the electrons don't receive enough energy to cross the gap. This inequality holds, and no photocurrent is detected. See how the electrons don't have enough energy to cross the gap. The potential difference for which the photocurrent stops is called the stopping potential and obeys this equation. If we measure the stopping potential for different frequencies, we can draw a graph of stopping potential against frequency to determine the relationship between the light frequency and the photon energy. As you can see, the stopping potential is proportional to frequency, which suggests the energy of the photon is proportional to the frequency. We can define the proportionality constant h, or Planck's constant. By relating this graph to a general linear graph, we can work out Planck's constant from the gradient. Rearranging the conservation of energy equation and expressing the photon energy as hf, we get this equation, which looks like the straight line equation. Hence, the gradient is equal to Planck's constant divided by the electronic charge. So by simply measuring the stopping potential for different colors of light and drawing a graph, we have been able to measure Planck's constant, the fundamental constant that governs the quantum world. The offset of the graph is related to the work function of the metal by this equation. These are the key points. When light shines on a metal surface, the photons deliver energy to the electrons in the metal lattice. If the energy of the photon is sufficient, the electrons receive enough energy to be released from the metal, with a little kinetic energy to spare. This spare kinetic energy can be measured. If the stopping potential is measured for different frequencies of light, we discover that E equals hf. And here are three features of the photoelectric effect that point to the quantization of light. 1. The photocurrent starts as soon as the light is switched on, so the light isn't building up wave energy on the plate over time, but delivering it as little packets to each electron right from the start. 2. Unless the light is a high enough frequency, no electrons are released, regardless of intensity. 3. For monochromatic light, the electrons all receive the same energy. That's about it for the photoelectric effect. Thanks for watching this tutorial.
Okay, so getting back to our whiteboard, or rather our slideshow. Again, Einstein did most of the work behind this. So the basic idea is that light can eject electrons off of a surface, but there's a minimum energy that's necessary for light to emit the electrons, or to eject the electrons off of the surface. And it turns out that there is a maximum wavelength or a minimum frequency that the light needs to have in order for electrons to be ejected. That if you go above a certain wavelength. So you get, so you use red light, for example, you don't get any electrons off onto the surface. So what is happening? So the light can eject electrons, and so you have a, and we'll actually be doing a similar experiment to this within a couple of weeks. And so the light ejects electrons. The electrons have a certain amount of energy. If they're being slowed down through a potential difference, there's a minimum amount of energy they need to have to get to the other side. And so that minimum energy is called the stopping potential. And if they don't have, if they have less energy than the stopping potential, they don't make it to the other side. So it turns out that um, what happens is if you shine high intensity light that's of a wavelength that's strong enough to eject electrons, um, you'll get a stronger current, at least up to a point. Whereas with lower energy electrons, you get a bit less of a current. And but beyond a certain voltage, you get a consistent amount of uh, the amount of current no longer changes. So it increases once you go up above the stopping potential, but then it flattens out. So why is this? And again, this explanation comes from Einstein. He was working on this more or less concurrently with this theory of special relativity. And like I said, believe it or not, it was for this that he actually won the Nobel Prize, not for special or general relativity. But the basic mechanism is this: that light can be treated as discrete particles called photons. The photon of energy, the photon of light can give all its energy, so that's E is equal to H times the frequency. The frequency can also be written as C divided by the wavelength. So the energy can be written as E is equal to HF. It can also be written as HC over lambda, where C is the speed of light and lambda is the wavelength. So the work function is the energy an electron needs to break free from the metal. So if the energy of the photon is less than the work function, you don't eject the electron. The electron absorbs the energy, but it's not enough to escape the atom. And that light will eventually get emitted back out. And so only photons with a minimum frequency equal to the work function divided by H can liberate electrons. So you have the cutoff frequency, the minimum frequency, where you can liberate electrons. And that corresponds to a maximum wavelength. So you go above that wavelength, the photons are no longer energetic enough to overcome the work function. And so the maximum kinetic energy is equal to H times F, the energy of the photon minus the work function. And so again, the energy of the photon is E equals HF, or E equals HC over lambda. And it turns out that the momentum of the photon can be expressed as P equals H divided by lambda. So you have this relationship between the wavelength of the wavelength of the light, or the wavelength of the photon, and its momentum. And again, the greater the frequency or the smaller the wavelength, the greater the momentum of the photon. In fact, Einstein used that relationship with the energy of the photon and the momentum of the photon to derive, at least in part, his E equals mc squared relationship. That if photons have energy that's equivalent to an amount of mass, then maybe a mass, something that has mass has an equivalent amount of energy. And that came ultimately, or at least initially, from this relationship. So special relativity and the photoelectric effect weren't necessarily completely independent of each other. So let's go to another example. Calculate the momentum of a photon of yellow light of wavelength 6.20 times 10 to the negative 7 meters. That's 620 nanometers. So let's set up the whiteboard. P is equal to h over lambda. And so let me write that better. P is equal to 6.626 times 10 to the negative 34 joules per second. And you're dividing by the 6.20 times 10 to the negative 7 meters. And so you get a wavelength in terms of kilometer or kilogram meters per second. And so that corresponds to 1.07 times 10 to the negative 28 kilogram meters per second. Okay, so getting back to the lecture. What minimum frequency of light is needed to eject electrons from a metal whose work function is 4.8 times 10 to the negative 19 joules? So you need a certain frequency to break that, to eject those electrons. So getting back to the whiteboard, we have HF is equal to E. And so we want to set, and so the minimum frequency is directly related to minimum energy. And so we can write the frequencies being equal to E divided by H. And so that's 4.8 times 10 to the negative 19 joules. And again, you're dividing by Planck's constant, 6.626 joule seconds. So your answer is going to be in inverse seconds or hertz. And it corresponds to 6.04 times 10 to the 11 hertz. If you want to figure out what the wavelength of that is, you just invert it and multiply by C, and you get 4.96 or 4.97 times 10 to the negative 4 meters. So this is an infrared wavelength. And visible light is on the order of 10 to the 14 hertz, at least as far as its frequency goes. So you're at about 1,000th the frequency you need to have visible light. And which means you're about 1,000 times the wavelength you need for visible light. Okay, getting back to the slideshow. That brings us to the Compton effect. And this was something else that had been observed in experiments that required a quantum explanation. So X-rays incident on a block of graphite get scattered with a longer wavelength or less energy than they started with. Now, it's not a large amount of energy. So basically what happens, the X-ray is incident on a block of graphite. If it collides with an electron, they will bounce in different directions. The X-ray will have its wavelength shifted, and uh, its wavelength will increase, so its energy will decrease, and but it's only a slight amount. So the shift in wavelength is a small fraction of the actual wavelength, but that wavelength goes in one direction, the electron goes in the other direction. And so the explanation is that the photon carries both energy and momentum. And then the collision is considered to be elastic, meaning kinetic energy and momentum are both conserved. And as a and so as a result, you can figure out the relationship between the initial wavelength and the final wavelength, again, working sort of under the assumption that uh, the change in the wavelength, or the delta lambda, is small compared to, it's a small fraction of the wavelength. So this is basically what happens. You have the light come in. Here's the electron. The electron gets scattered at an angle phi. The wavelength gets scattered at an angle theta, but it has a new wavelength. And again, it's a higher wavelength corresponding to lower energy. So how do you figure out what that is? So let's go to the whiteboard. And again, what you have here is an elastic collision. So momentum is conserved and energy is conserved. So you basically have three equations. You're not ultimately interested in the velocity of the electron going out, or even the scattering of the electron going out. You're interested in the relationship between lambda prime and theta, the scattering angle of the wavelength. So you have the electron. The wavelength comes in, or the photon comes in, the photon goes out, and the electron goes out. So this is angle phi, and this is angle theta. So what do we know? Well, momentum is conserved, and it's conserved in both directions. So we'll define the x direction as the initial direction of the photon. So pxi is equal to h divided by lambda naught. So we have lambda naught and we have lambda. So lambda is going to be the final wavelength. And we're interested in the shift of the wavelength. The final momentum in the x direction is equal to h over lambda, but you need the x component. So that's cosine theta. So that's the momentum of the photon plus the momentum in the x direction of the electron. And then in the y direction, well, there is no momentum initially in the y direction, so that's 0. And the final momentum is equal to h over lambda times the sine of theta minus, because it's going in the opposite direction, mv times the sine of phi. And then it's an elastic collision. So the initial kinetic energy is hc for the kinetic energy over lambda naught, and the final kinetic energy is equal to 1/2 mv squared plus hc over lambda. And again, it's an elastic collision. Kinetic energy is conserved. So how do you go about solving for this? So we can use this equation to solve for the sine of phi, phi. So the sine of theta, remember the final momentum has to be 0, or the total final momentum has to be 0. So the sine of phi is equal to h over mv lambda times the sine of theta. And from a trigonometric identity, we can write this as the square root of 1 minus the cosine squared of phi. And the reason we're going to do that is so that we can put that relationship in here at some point. And so that, you can, you can get in order to eliminate the phi term from the equation. So you need to turn this into, you want to solve this equation for the cosine of phi. So the first thing you do is square both sides. So we have h squared over m squared v squared lambda squared sine squared theta is equal to 1 minus the cosine squared of phi. And from that, you get the cosine of phi is equal to the square root of 1 minus h squared m squared v over m squared v squared lambda squared sine squared phi. Or sine squared theta, excuse me. And that's something you can plug in here. So the initial momentum is h over lambda naught. And I'm going to need to erase a few things to clear some space. So h over lambda naught is equal to h over lambda cosine theta plus mv times the square root, times this big square root. So 1 minus h squared over m squared v squared lambda squared sine squared theta. And now we're going to clear out everything over here. And we're going to keep working on that. So we're going to isolate the square root term because ultimately we want to square both sides. So we have h over lambda naught minus h over lambda. Remember, lambda has a greater wavelength, so a smaller energy. So this is going to be a positive term, and that's h over lambda cosine theta is equal to mv, and again times that big ugly square root. Okay, so now you square both sides. So this term is a little bit long, but you'll see that eventually you get some simplification out of this. So h squared over lambda naught squared minus 2h squared over lambda naught lambda plus, or cosine theta, don't forget the cosine theta, plus h squared over lambda squared cosine squared theta is equal to m squared v squared and so again, you square these terms out. So you have m squared v squared, and then you have minus h squared over lambda squared sine squared theta. So, you square both sides. So you have m squared v squared, and then you have that square root. So you multiply m squared v squared by 1, you get this. And then you multiply m squared v squared by that. Well, the m squared v squared terms cancel out, and you just left with a squared over lambda squared sine squared theta. Now that's something you can work with even further, because if you notice, if you add the h squared over lambda squared sine squared theta to h squared over lambda squared cosine squared theta, you're just left with h squared over lambda squared. So you have h squared over lambda naught squared minus 2h squared cosine theta over lambda naught lambda plus h squared over lambda squared is equal to m squared v squared. And you can approximate that. Again, what we're going to do here is that, again, we're working on the assumption that the change in wavelength, so lambda minus lambda naught, is a small fraction of the actual wavelength, so that lambda naught and lambda are approximately equal. So we have m squared v squared is approximately equal to h squared over lambda naught squared. And you can write it as lambda naught squared or lambda squared. It doesn't really matter. Multiplied by, and so there's actually a 2 in here as well, because you add these together, you get then 1 minus the cosine of theta. So you can see things are already starting to simplify. And so that brings us to the third term in this. HC over lambda naught is equal to 1/2 mv squared plus hc over lambda. And so we'll now erase the left side of the board, since we have everything we need there. And so this is the energy conservation. This is where the elastic collision part comes in. So we can write this as hc over lambda naught minus hc over lambda is equal to 1/2 mv squared. So you can think of 1/2 mv squared as being equal to m squared v squared, which we know, which we already have a value for, divided by 2m. So you multiply the numerator and the denominator by m, and you still have that 2 that you need to take into consideration. So we can write that as, so the 2's cancel out, and you have h squared over lambda naught squared, 1 minus the cosine of theta. Okay, so let's simplify this. So reducing that to the lowest common denominator. So we have lambda naught lambda. You can write that as h times c, and then you have lambda minus lambda naught. So basically just simplifying this. So 1 over lambda minus 1 over lambda naught minus 1 over lambda becomes lambda minus lambda naught over the product of the two. And that's equal to h squared over lambda naught squared um, and there should be an m here. So h squared over the mass times lambda naught squared times 1 minus the cosine of theta. So again, taking advantage of the fact that these lambda and lambda naught are essentially or approximately equal, that this lambda minus lambda naught is tiny compared to a small fraction of the absolute value, that you could write lambda naught lambda as lambda naught squared, lambda naught times lambda as being approximately equal to lambda naught squared. These terms cancel out, and one of the h terms cancels out. And what you're left with is lambda naught, or rather lambda minus lambda naught. So the shift in the wavelength is equal to h over mc, where m is the mass of the electron and c is the velocity of light, times 1 minus the cosine of theta. So you can relate the shift in the wavelength to the scattering angle theta. And so that's what Compton was able to do. He was able to derive this equation using momentum and energy conservation. And so you get this. So delta lambda is equal to lambda prime minus lambda naught, or simply lambda minus lambda naught. And that's equal to h times the mass of the electron times c multiplied by 1 minus the cosine of theta. And this term is a constant term. Planck's constant we know, the speed of light we know, and the mass of the electron we know. And so that comes out to be approximately 0.00243 nanometers, and that's called the Compton wavelength. And so you take that number and you multiply it by 1 minus the cosine of theta. And so there's a direct relationship between how much the wavelength of the X-ray, the incoming X-ray gets shifted, and how much of the incoming X-ray gets shifted, and the angle at which the X-ray gets deflected. So let's go to an example. A high frequency photon is scattered off an electron and experiences a change of wavelength of 1.5 times 10 to the negative 4 nanometers. At what angle must the detector be placed to detect the scattered photon relative to the direction of the incoming photon? So basically, what is theta? So, clearing all this out, so we have lambda minus lambda naught is equal to, we'll call that lambda c for the Compton wavelength, 1 minus the cosine of theta. And so we want to solve this for the cosine of theta. So divide both sides by lambda c. And that's equal to 1 minus the cosine of theta. So the cosine of theta is equal to 1 minus lambda naught over the Compton wavelength. And so then theta is equal to the inverse cosine of 1 minus, again, lambda minus lambda naught over lambda c. And so now we can plug those numbers in. 1 minus, and so the shift, we are told, is 1.5 times 10 to the negative 4 nanometers. And the Compton wavelength, going back a slide, is equal to 0.00243 nanometers. And so the angle shift is 20, and it's only two significant figures, so 20 degrees. So the wavelength is shifted by that amount, and it's the angle at which uh, the photon will be scattered is 20 degrees. And that's 20 degrees relative to the horizontal. So EM radiation has properties of both waves and particles, but does it work the other way around? Can particles have properties like waves? And it turns out the answer to that is actually yes. And de Broglie, a French scientist, figured out that, well, if the wavelength of a photon can be expressed as h, or rather the momentum of a photon can be expressed as h divided by lambda, you can talk about the wavelength of an object as being equal to h divided by p, where p is its momentum. And that also it has a frequency equal to E, its energy, divided by h. In that case, E divided by Planck's constant. So you have, its momentum, and E in this case is its kinetic energy. And so that's been shown that you can fire electrons through a double slit pattern or through crystals, a crystal lattice, and get an interference pattern out. That the electrons will interfere with each other so that you get the beams, and the intensity doesn't steadily decrease from the maximum, but rather you have peaks, a maximum, a minimum, a maximum, a minimum, and so on, that you get wave-like properties, and you get interference, and you can do that using electrons. So we're asked, calculate the wavelength of a 0.23 kilogram ball traveling at 0.10 meters per second. So we're looking at a real world object and velocity and figuring out its wavelength. So again, P is equal to H over lambda, and we are asked for lambda. So lambda is equal to H over P. And its momentum. So P is equal to mv. This is an object with mass moving at a subrelativistic speed. So 6.626 times 10 to the negative 34 joule seconds. And you're dividing by the mass of the object, which we are told is 0.23 kilograms, and the velocity, which we are told is 0.10 meters per second. And you can see, probably even before you do the calculation, that this number is going to be way too small, especially at the real world level, to produce a noticeable effect. But as the mass of the pot, as you go to the atomic level and the mass of the objects you're looking at gets smaller, then you see wavelengths that are significant compared to the size of the object in question. That's definitely not going to be the case here. So that's Planck's constant divided by the mass and divided by the um, velocity. And that gives 2.9 times 10 to the negative 32 meters. So that's not a significant wavelength. It's really not a significant wavelength at the real world scale, but in principle, if you could measure things at the real world on that level of precision, you could observe the effect. All right, let me. Okay. All right. So moving. All right. So another example before we move along. Through how many volts of potential difference must an electron be accelerated to achieve a wavelength of 0.21 nanometers? So we will assume, for the sake of simplicity, that we're talking non-relativistic speeds, and we can verify that basically less than 1/10 the speed of light. And we want to achieve a wavelength of 0.21 nanometers. So we're asked through how many volts. Um, and so the energy that an electron gains as it travels through a potential difference is equal to its charge multiplied by the potential difference. Um, and if you want to be technical, you could write that as negative QV, but ultimately it's going to gain. The whole point is we're gaining energy. So E times V is equal to the kinetic energy that it gains. So the electrical energy becomes kinetic energy. So we can write that. And since we want the momentum and we need the momentum, so we can write that as P squared over 2M. So that's the classical momentum of a an electron. And so the momentum, we can then write that as H squared over 2M lambda squared. And we'll have a delta V for the potential difference. So now we can write that. Delta V is equal to H squared over 2ME lambda squared, because we were given the wavelength. And so we've expressed things in terms of the variables we need. So that's 6.626 times 10 to the negative 34 joules second, and you're squaring it. And you're going to have to be careful some of the time when you're working with Planck's constant. Usually the calculators don't go beyond 10 to the negative 100. So you may have to be careful with the calculations at some point. But then the mass of the electron is 9.11 times 10 to the negative 31 kilograms. E is 1.60 times 10 to the negative 19 coulombs. And then the lambda is 0.21 times 10 to the negative 9, because it's nanometers. And you're squaring that. So a lot of messy scientific notation. And you're squaring that. Okay, and then divide by lambda. And so when all is said and done, you get a voltage of 34 volts. Okay, just to double check that it is relativistic in case, or non-relativistic in case you were wondering. So the momentum is h divided by lambda. So that's 6.626 E34 negative divided by 0.21 E9 negative. So you get a momentum of 3.16 times 10 to the negative 24 kilogram meters per second. And then you're dividing that by 9.11 times 10 to the negative 31 kilograms. And you get 3.46 times 10 to the 6 meters per second. So it's less than a tenth the speed of light. So you're not at that critical level where you have to take relativistic effects into account. So if you did the relativistic version of this equation to two significant figures, you would still get 34 volts, although it might take you a bit longer to actually get there. Okay, so moving further. So another thing that people were noticing as they looked at uh, light given off by different substances is that the light was emitted at different wavelengths, but there was a characteristic spectrum for each light. So the question is why? And so any theory of the physics of the atom had to explain the observed spectra. And hydrogen, it was already understood that hydrogen was the simplest element, one proton and one electron. So you had to start there with hydrogen. So a spectrum is the list of wavelengths of electromagnetic radiation that a particular atom or molecule can absorb or emit. So it emits the same wavelengths that it absorbs. An atomic spectrum is not continuous, but it consists of discrete absorption or emission lines. So you're looking at hydrogen, helium, and neon, and you notice the different things, and this is in the visible part of the spectrum. And so this is the emission spectrum. And then if you look at the absorption spectrum, so you shine white light through hydrogen gas, you get this come out. You see the some amounts of the light are absorbed, and it's the same wavelengths. Hydrogen absorbs the same wavelengths that it emits, and that's true of all atomic and molecular spectra. That's they absorb the same wavelengths that they emit. Well, okay, why do you get this? Where do these values come from? And why? And so the beginning of that explanation came from a scientist named Rydberg. He came up with a mathematical relationship. So he was able to see a pattern in the wavelengths of emission. And this is not just the visible spectrum, but in the UV and the infrared as well. That he looks at the wavelengths of hydrogen, emitted by hydrogen. And he was able to figure out that there was a relationship 1 over lambda is equal to a constant multiplied by 1 over m squared minus 1 over n squared. So the constant, called the Rydberg constant, is 1.10 times 10 to the 7 inverse meters. But what are m and n? They're actually integers. The catch being n is less than m. So, and it turns out that n corresponds to n is greater than m, excuse me. So what happens is, the electron goes from energy state n to energy state m, so a lower energy state, and it's giving off light in the process. Well, okay, Rydberg was able to figure out the mathematical relationship, which was not a small accomplishment. It was a fairly significant accomplishment at the time, but he could not explain why that relationship worked. And the original explanation, that was modified as quantum mechanics developed, was given by Niels Bohr, a Norwegian scientist. So again, much like Einstein, he starts with a couple of assumptions and then goes where the mathematics leads him. So what are the assumptions? The electron moves in a circular motion around the proton according to the Coulomb force. So you've got an electron that's essentially in orbit. Now we know the picture is fuzzier, literally and figuratively, but the basic idea behind it still, the mathematics still works actually. So only certain orbits are stable and allowed. So uh, you can't just orbit at any radius. There are very specific radius values that the electron can have. The hydrogen atom emits radiation when the electron jumps from a higher energy state to a lower energy state. So Bohr could see from looking at the Rydberg equation that N corresponded to a higher energy than M. And going back to the previous equation. And so that's the emission of light corresponded to a change, or the emission of radiation corresponded to a change in the energy state. And here is the key assumption that made the mathematics work. The circumference of the orbit must contain a whole number of wavelengths. So 2 pi r, the circumference of the circle, is equal to an integer multiplied by lambda. So that whatever orbit you had to be a complete number of cycles. So how does that work? So starting with the potential energy, and so if you remember from physics 230, the potential energy of an electron in an orbit around the proton is equal to negative k, the Coulomb constant, times e squared. So uh, the charge of the electron is negative e, the charge of the proton is positive e. So together they're negative e squared divided by r. And that's assuming the potential energy is 0 at infinity. From centripetal acceleration, the centripetal force, mv squared over r, is equal to the Coulomb force, magnitude k e squared divided by r squared. And so the kinetic energy is equal to 1/2 mv squared, which is equal to ke squared over 2r. So you basically bring the r, multiply both sides by r, and then you multiply by 1/2. And so you get ke squared over 2r. So that's the kinetic energy. So the sum of kinetic plus potential is a negative number, negative ke squared over 2r. So the total energy is negative, again, because you have negative, you have a negative potential energy that turns out to be greater than the, or of a higher magnitude than the kinetic energy. So combining the de Broglie wavelength with postulate 4, so again, the orbit has to have a complete number of cycles. So 2 pi r is equal to n divided by lambda. Lambda is equal to h over p. And p in the classical version, and there is a relativistic version of quantum mechanics, that's a subject for a different chapter. So you can write 2 pi r is equal to nh over mv. So solving this for the velocity of the electron, so dividing both sides by 2 pi r and multiplying both sides by v, you get v is equal to n times h bar. So h bar is equal to the Planck's constant divided by 2 pi. So, in fact, let me just write that out so you get, okay. So you can see that. So the h over 2 pi is equal to h bar. And so you see that h bar come up a lot because there are a lot of circumstances where you need to divide Planck's constant by 2 pi. So you see that h bar term come up a lot. And again, it's equal to h over 2 pi. So the radius r then can be solved in terms of the energy state n and known constants. So we know that k is equal to 1/2 mv squared. So we use this value of v. And so we get k is equal to 1/2 mv squared, which becomes n squared h bar squared over 2mr squared is equal to ke squared over 2r. So we already had this value for the kinetic energy. So we can then solve this for n, or solve this for r. So the radius is equal to n squared over h bar squared divided by m k e squared. So we can solve for the radius in terms of n and known constants. And then we can solve for the energy in terms of n and known constants as well. So the total energy, again, negative ke squared over 2r, well, we've just solved for r. So we can plug that in. And so what we get is the energy is equal to negative m k squared e to the 4th divided by 2n squared h bar squared. So we can solve for the radius and the energy in terms of known constants. So the radius of the orbiting electron is equal to n squared times a naught, where a naught is the radius when n equals 1. And so that's equal to h bar squared over mke squared, which is equal to 0.0529 nanometers. So that's called the Bohr radius. So that's the radius of an electron in the lowest energy state around a hydrogen atom. And so that's been found to be an accurate value. And so the total energy is a function of n. So plugging all those numbers in and converting from joules into electron volts, you get E is equal to negative 13.6 electron volts divided by n squared. And so N1 corresponds to the ground state. And what the correspondence principle says, that quantum mechanics and classical mechanics agree when the difference in energy levels is small. So the ground state is a term for the lowest possible energy. So an electron can never have zero energy. It has to have a minimum amount of energy. And so you put these in, and actually you get the Rydberg relationship out when you do the conversions. So you're going from one energy state to another energy state. And you get, like I said, you get the Rydberg term out. The limitations of the Bohr model are that it only really works in one electron atoms. That as the configuration gets more complicated, you need something else. And it also turned out that for a given value of n, there were additional sublevels for that. And those are things we'll talk about as we talk about the Schrodinger equation and get into what we think of now as quantum mechanics. So how does this look? So the Lyman series, so you see the Lyman series are wavelengths of radiation emitted by hydrogen, where the n state is the ground state, n equals 1. So these energies are actually correspond to ultraviolet wavelengths. So the Lyman series doesn't correspond to the wavelengths that we see. The Balmer series actually corresponds to wavelengths that we see. So n equals 3 to n equals 2, n equals 4 to n equals 2, n equals 5 to n equals 2, then 6, then 7. So the wavelengths of light that hydrogen emits that we see correspond to the Balmer series. So electrons going from a higher excited state to n equals 2. And then the Paschen series is from higher energy states to n equals 3. So, again, uh, Bohr's model works perfectly well for hydrogen. It works perfectly well for helium with one of its electrons removed, and lithium with 2 of its electrons moved. But for um, but for more complicated configurations with multiple electrons, you need something else. So with that, let's go to some examples and then we'll be done for today. So for the 3 hydrogen transitions indicated below, with N being the initial state and N prime being the final state, is the transition an absorption or an emission? So if it's an absorption, you're increasing energy levels, or you're going to a higher energy level. And if you're emitting radiation, you're going down to a lower energy level. Which is higher, the initial state or the final state energy of the atom? And finally, which of these transitions involves the largest energy photon? So going from n equals 1 to n primed equals 3, you're gaining energy. So that's a photon is absorbed, you're going to a higher energy state. N equals 6 to n primed equals 2, that's emission. You're emitting a photon and going down to a lower energy state. N equals 4 to n primed equals 5. That's going, again, absorbing and going to a higher energy state. And then finally, which of these transitions involves the largest energy photon? And you might think from looking at this, well, n equals 6 to n primed equals 2. That's not actually true. And I'll show you that. So you have the energy of the photon is equal to negative 13.6 EV 1 over n final squared minus 1 over n initial squared. Or in the way it's written, 1 over n prime squared minus 1 over n squared. And so for A, that equals and so if it's negative, the way I've written it corresponds to absorption. Actually, I got the prime in the wrong place. Now it corresponds to absorption. So for the first one, it's going from 1 to 3. So that's so for the first one, that corresponds to negative 12.1 EV. And again, the way I have it written, this would normally be the energy that the photon that's emitted. And you can also write this as 13.6 EV 1 over n prime squared minus 1 over n squared. So if it's negative, you're not emitting, you're absorbing. So that's 12.1. B, you're going from 6 to 2. And that corresponds to 3.02 electron volts. So that's only a quarter of the energy of the 3-to-1 jump. And so it's about 4 times greater wavelength as a result. So again, this is a Lyman series transition, and this is a Balmer series transition. And then the last one, you can probably already tell, is not going to be that big of a jump. So that's 4 to 5. So that's negative. And again, the negative means it's emission, 0.306 electron volts. So it's, again, negative means the photon is absorbed rather than emitted. And so you have a very high energy photon absorbed in part A, a relatively lower energy photon is emitted in part B, and then a significantly lower energy photon is absorbed in part C. So let's move on to the next problem. How much energy is needed to ionize a hydrogen atom in the n equals 3 state? So what's meant by ionization? That happens when the photon gets enough energy that it's kicked out of the, enough energy to escape or rather the electron gets enough energy to escape the pull of the proton, and it escapes the atom. And so that happens when the total energy is 0, when the kinetic energy equals the potential energy. And when that is the case, and so when the total energy is equal to 0 at that point, that's when you have enough energy to get out of the escape the atom. So basically, the energy in state 3 is equal to negative 13.6 electron volts divided by 3 squared. So that corresponds to the n equals 3 state. And so that's the total energy, kinetic plus potential. And so that corresponds to negative 4.53 electron volts. And to go from electron volts to joule, you're multiplying by E, or 1.6 times 10 to the negative 19. So that's the energy in state 3. So what the ionization means, you need to absorb enough energy so that your total energy equals 0. So you need a photon with 4.53 electron volts or more to come along and be absorbed by the electron, so that it then gains enough energy that it can leave the atom. Anything less than that will keep it within the atom and kick it up to a higher energy state. But it'll kick it up to a higher energy state, but it won't be enough to enable it to escape the atom. And so the last thing we are going to go over determine the wavelength of the second Balmer line, n equals 4 to n equals 2 transition, and then determine likewise the wavelength of the third Lyman line and the wavelength of the first Balmer line. So again, Lyman is n equals 1, or n final equals 1. Balmer is n final equals 2. So let's do this. So the first Balmer line is n equals 3 to n equals 2. The second Balmer line is n equals 4 to n equals 2, and so on. So the third Lyman line, so the first is n equals 2 to n equals 1. The second is n equals 3 to n equals 1. The third is n equals 4 to n equals 1. So again, getting back to this, so the energy of the photon, which is what we're asked so hc over lambda, the energy of the photon, and ultimately we want to solve for lambda, is equal to the energy of the initial state, which is higher, minus the energy of the final state, which is equal to negative 13.6 eV times 1 over n initial minus squared minus 1 over n final squared, which is equal to 13.6 eV 1 over n final squared minus 1 over n initial squared. So we'll start with part A. So n initial is equal to 4, n final is equal to 2. So the first thing you do is solve for hc over lambda using that. 13, so that's 2.55 electron volts. And we want to convert that to joules in order to use SI units. We want to convert that to SI units here. So that's 1.6 times 10 to the 19. So that's 4.08 times 10 to the negative 17 joules. Actually, hold on. That's 2.55 electron volts. That's 4.08 times 10 to the 19 joules, excuse me. All right. So that's times 10 to the negative 19 joules, which means lambda is equal to hc over 4.08 times 10 to the negative 19 joules. And so what you get from that 4.9 4.90 times 10 to the negative 7 meters. That's 490 nanometers. That's visible. And again, it's the Balmer lines that are the visible lines. So that's sort of in the blue-green region of the spectrum. So let's, if we go back to a couple of slides. Okay. You go back here, that corresponds to this. And so that's one of the Balmer lines. All right, so moving along, or moving back, now we have the wavelength of the third Lyman line. So that's Ni is equal to 4 again. But now N final is equal to 1. So you repeat the process. So that's right there. So that's 12.8 electron volts, which equals 2.04 times 10 to the negative 18 joules. And so that gives lambda is equal to, again, you're multiplying HC, or you're dividing H times C by this number. So you're getting 9.74 times 10 to the negative 8 meters. So basically 1/5 the wavelength of this, and that's in the ultraviolet, the more energetic photons. And then for the last one, that's the first Balmer line. So that corresponds to n initial is equal to 3, and n final is equal to 2. So HC over lambda is equal to okay. So it's equal to 1.88 electron volts. And in terms of joules, that's 3.02 times 10 to the negative 19 joules. And so lambda, then you divide HC by that number. And you get 6.58 times 10 to the negative 7 meters. And again, that line is visible. So if you go back to the slideshow and go back to that screen, or that shot with the spectrum, you see 658 nanometers. That corresponds to the red line. So again, that's also in the Balmer series. So this is the first Balmer line. This is the second. This is the third. This is the fourth. And you can go on from there, but this is the last one you're likely to be able to see. Okay, so we're done for today. Friday, we will again meet in person. And so we'll go over some problems from this chapter, and we'll also continue with the experiment from last week. So good luck with everything, and I'll see you soon.